Hey guys, so welcome back. This is actually my second graphing rational functions video, but I think this time I'm going to go into a little bit more Hi you guys, welcome back. So today we're going to be talking about graphing rational functions and just some properties of rational functions in general. So when we take a look at rational functions, let's look at what those exactly are. So a rational function is going to be a ratio of polynomials. So we just finished learning about polynomials in terms of the curriculum for my class, and we'll take a look at what those look like. So a ratio of polynomials are going to look like your typical, you'll have some real number coefficients in this class. In most pre-calc curriculums, you're only going to be dealing with real numbers for the coefficients, and then you'll have powers of x. So this is the fancy way to write out polynomials. And what this notation boils down to is just you've got real number coefficients and positive integer values for your degrees on your x's. So something along those lines. And in general, people will tend to write these as p of x over q of x, just like how with variables we tend to use x, y, and z. With polynomials, we tend to use p, q, r, s, and t, I would say, is our most common polynomial names. So in general, a rational function is a ratio of polynomials, but that doesn't mean that that's the only way that they could be handed to you. So it means that any function that could be put into this format is a rational function. So let's look at the three most common formats you'll see of these rational functions. The first one would be a factored rational function. That's going to be our most convenient, I would say, for graphing, in my opinion. So let's say, for instance, our f of x looked like we'd have our numerator factored and our denominator factored, like that, which is clearly different than just having a sum of terms. So format 2 would be an unfactored polynomial. So something like g of x equals x squared minus 2x plus 1 over x squared minus 4. We can see the difference here between a factored versus an unfactored polynomial. We have a product for the factored version and a sum and difference for the unfactored version. So hopefully we're getting a little bit better at noticing the difference between those two. Okay, and then our third format, which I figured we've already kind of talked about it in our graphing with transformations unit, but we're going to get a little bit of review in some of the homework for this particular unit. And a rational function can also be written in kind of what I think of as the transformation format. There's no official title for this, but if you see a function that looks kind of like this, let's say it's h of x equals negative 2 over 3x plus 5 minus 6. Okay, we covered this kind of rational function when we were talking about graphing with transformations, because this format lends itself well to looking at the parent function, 1 over x, and then identifying your transformations that have been applied, which I call here a, b, h, and k, just like how we learned, and then doing our transformation. So there's a couple problems just to review that and keep it kind of fresh in your brain as a tool, but not all rational functions are going to lend themselves well to this graphing technique. And so as a result, it's not our main go-to tool for graphing in general. It's just kind of like a handy tool that we keep in our back pocket that works sometimes. So we'll just say that for how to graph this, we graph these with transformations. And when you get to those problems reviewing that, remember we covered transformations. It's 1.7 in our textbook, but if you're working out of a different pre-calc textbook, then Stitz-Zager. You'll have probably covered this in, whatever unit you do the graphing with transformations. And I have a video on my YouTube channel about graphing with transformations, a couple of them actually, where you can review this process. So this video is going to focus mostly on graphing format number 1 and format number 2, our factored and unfactored rational functions, versus graphing with transformations. So let's look at just in general how we would graph these two. We're not going to use transformations. Okay, it's not well suited. It's not a well-suited tool to the bulk of these kind of rational functions. So we won't graph these with transformations. Instead, we're going to learn an alternate process. Okay, now our textbook calls it a 6-step process, and that is by no means completely general. So depending on what textbook you're learning out of, they might call it something different. But in general, the idea of what the properties we are looking for are stays the same. So we'll just call this unit, how we graph rational functions in general. And there's not really a set name for what this is called, like graphing with transformations. Okay, so let's look at the steps for what we're going to be looking for. So first thing that we're going to be looking for is we're going to want to find the degree of the numerator and the denominator. So from our polynomial unit, you might recall that the degree of the numerator and denominator is the power on the leading term. So if we go ahead and look up at our two different format 1 versus format 2, I would say it's a little bit easier to see the degree on format 2. The degree for the numerator here would be 2, and the degree for the denominator would be 2. We can still figure out the degree with format 1 though. We kind of practiced doing that when we covered graphing with polynomials. We figured out what the leading term is by calculating the product of the leading term. So we could still figure out that for f of x, the leading term would be x squared, so the degree would be 2. And for the denominator, same idea, x times x would give me x squared, so the degree for the denominator would be 2 as well. And we'll get some practice on specific examples doing that. This is just kind of a preview. So the reason that we're doing this is because before we jump into factoring, if you have something that's unfactored, I think it's helpful to identify the degree right away and to use that to determine any sort of end behavior. So with polynomials, we had our little tricks for figuring out whether the polynomial had left end behavior and right end behavior of positive or negative infinity. But for these rational functions, it's not necessarily plus or minus infinity. In fact, for a lot of the examples we're going to see, it's not going to be plus or minus infinity. So I want to have you getting that in your mind right away, knowing that, okay, these are going to have a slightly different behavior than polynomials because they are a different type of function fundamentally. So we're going to do that first, identify the degree, and have at least in our mind what kind of end behavior we are looking for. Then from there, we're going to find the zeros of the denominator and numerator and reduce. So if at all possible, we will factor this and then reduce any like factors. But we want to know what the zeros are before we do that. So we want the zeros of the numerator and denominator, and then we're going to reduce. Okay, next what we're going to do is we're going to figure out if this happens to have what we call a horizontal asymptote, we're going to find any intersection points of that horizontal asymptote. And then for the fourth step, which is not always going to be necessary, but will sometimes be helpful, you can either use a sign chart or you can plot a few more points manually by building a t-chart to determine the general shape. One option is the y-intercept. A lot of people like to find that. Sometimes I don't find the y-intercept particularly the best point to plot, but it's definitely a property that some people are interested in plotting. So we'll see kind of on a case-by-case example when it's helpful to get more points to graph. Okay, so in general, that's going to be how we do these. Now, the first thing people always want to know when we're talking about graphing is how is this going to compare to something I would see on, say, Desmos or a graphing calculator. So why would we even want to practice sketching these without just blindly looking at technology? Which is a great question, because technology, as you guys know, I believe technology is a very helpful tool, and we're moving into a very technological era as a society. So I don't discourage the use of technology, but with graphing these sorts of functions, there are just certain things your calculator is not going to show you. So we've already seen some trivial examples, and I've kind of pointed it out, but I want to remind you. Okay, graphing calculators are never going to tell you arrows. Okay, and that might seem kind of trivial, but what that means is that your calculator is not really making any sort of commitment as to end behavior. It's just a picture that you could continue to zoom out to hopefully see the pattern, but you're not going to see arrows. You're not going to see a clear statement of any sort of end behavior. So end behavior is something that it's kind of up to us to make that judgment call. Okay, what else are we not going to see? We're not going to see asymptotes. Okay, no graphing calculator or Desmos plots asymptotes for you. You'll notice the curve approaches the asymptote after you know the asymptote exists, but you kind of have to be on the lookout for that asymptote in the first place. So that's both vertical and horizontal asymptotes. Your graph is going to choke on that. And here's the really misleading thing, because you would think that it could handle graphing this, but any sort of hole in your function, and we've seen it with piecewise functions at this point, and we'll see another kind of hole happening with these rational functions, but whenever we have those open points, those are considered a hole in the graph. It's not actually a real point, and because it isn't a real point, what your calculator does is it just goes ahead and connects the curve through the hole. So when you look at the picture, you're not going to see it whole and all. You're not going to know that it exists. It's going to be something that you just have no idea of unless you already know to look for it. Then if you know to look for it, you can probably check on the t-chart and see, oh, the calculator did know it was undefined, but it just can't show that on the picture. So those are kind of the main culprits for what Desmos will not show you. We also just want to be comfortable understanding things like what x values are in the domain, what x values are undefined, have those kind of properties in our mind when we jump into calculus and we have to work with these functions. So just a pointer as to the shortcomings of technology on this particular type of function. So let's jump into graphing some examples of these. We're going to sketch the following rational functions, and we will answer the following questions about the properties of the graph. So the properties that we're just going to make special note of are the domain, the range, any undefined x values, what was the end behavior, the x-intercept, and the y-intercept. And I'm just asking you these questions to get practice with this vocabulary, and there are certain things that are important properties about the rational functions. So to get started, our first example is going to be f of x equals x squared minus 2x plus 1 over x cubed plus x squared minus 2x. So let's jump in and identify degree. Okay, so the degree for the numerator would be 2, and the denominator for the bottom would be 3. Okay, so when we think about end behavior, as I've kind of hinted at, this is not as easy as just saying plus or minus infinity, because we have a fraction now. So when I go ahead and plug in a large x value, we're going to see that these fall into a somewhat predictable pattern. We have 3 possibilities. So possibility number 1 is that you have, like in this instance, you have the degree of the denominator being bigger. And when we fall into this case, what we're going to see is that when I plug in, let's say for the right end behavior, I'm going to plug in a very large x value. If I plug in a very large x value, we don't really have to pay too much attention to the subsequent terms. We're going to pay a lot of attention to those leading terms, x squared and x cubed, because those are going to really determine the behavior of this function. And we'll write out one example and you'll kind of see why. When I plug in 100 squared, it's going to so far outweigh the following terms that it's kind of like that negative 199 doesn't really matter compared to the 100 squared. But you see what you end up getting is these fractions, and fractions are not going to tend towards infinity. What they're going to end up tending towards, so highlighting what's going to really dictate this, is we're going to tend towards 100 squared over 100 cubed. So it's going to be acting like that. Okay, now think about having more and more, like if I plugged in 1,000, what's going to happen is you're going to have more and more zeros. And what's happening is the bottom is far outstripping the top. The bottom is far outpacing the top. So these fractions are going to approach 0. Okay, don't believe me? You can compare that to 1,000 squared over 1,000 cubed, and you're going to see an even smaller fraction than last time. So you'd have 1, 2, 3, 4, 5, 6 over 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and the zeros would cancel again. So 1 over 100 compared to 1 over 1,000. You guys see the pattern. You've got these fractions that are approaching 0, as I said. Okay, so what is our takeaway from this? Because I don't want you guys to have to, do this tedious process of plugging in an x value every single time to get the end behavior. The pattern that I want us to observe is that when the numerator degree is smaller, we're going to have end behavior of the y values are going to go to 0. So this is going to be an example of what we call a horizontal asymptote. Our curve is going to approach a horizontal line at 0. Okay, let's highlight that. That's kind of our, if you guys were making a little cheat sheet and you just wanted to have things like quickly summarized, that's how I would summarize this. So I'll leave you guys to check manually the left end behavior. I swear that it's also going to approach 0, but like I said, you can go ahead and check that. So we know we're going to have a horizontal asymptote at y equals 0 for any time we look and we see that the numerator has a smaller degree than the denominator. So this is case 1, and in our next examples, we'll see cases of the other 2 situations. Okay, so we've got the end behavior that we need. Next, let's go ahead and dive in and find the zeros of the numerator and denominator, because those are going to be pretty important properties of the graph as it would turn out. So the zeros of the numerator, just like we practice with our inequality test, factoring is going to be the way to go whenever you can do it. So these are particularly, I would say, easier to factor polynomials, but we learned some advanced factoring techniques in our previous unit. So when we factor that numerator, we get x minus 1 squared. So our zeros would be 1. And the zeros of the denominator, when we factor our denominator, it looks like we end up getting x times x squared plus x minus 2, and we can factor that even one step further into x plus 2 times x minus 1. Okay, and if factoring is a little bit of a weak point for you still, feel free to look at some of my factoring videos on this channel, and also there's a lot of cool YouTube videos on factoring in general by some other creators. So the zeros of the denominator are going to be 0 from this first factor, and then negative 2 from the second factor, and then 1. Okay, so you see how we have an overlap there? We have a factor of x minus 1 on the top and bottom. So let's go ahead and note that we have that and go ahead and reduce this rational function. So we have x minus 1 times x minus 1 in the numerator, and in the denominator we have x times x plus 2 times x minus 1. Okay, so we have that repeat factor here. X minus 1 over x minus 1. So the question is, what happens when we have something like that? We want to know what that visually looks like on the graph. So when you have a repeat factor like this, what that means is you're going to have what's known as a hole at x equals 1, because when I try and plug in x equals 1, I get division by 0. So if I get division by 0, it's not a value in the domain. We've already seen that previously. And the fact that there's another factor in the numerator that's x minus 1, that's beat out by the fact that there's division by 0 that's happening there. So what you look at is you completely try to reduce any factors you can, and then you look at what's left over. So the fact that we were able to reduce out the x minus 1 in the denominator means we have a hole there. So we got a hole at x equals 1 because factor and denominator canceled completely. Okay. And again, we're kind of taking some properties. I'm kind of letting you guys use a little bit of patterns here, but if you checked me with a t-chart and started plugging in x values really close to 1 on the left and right, you'll notice that we're approaching a particular finite number, like they're getting closer and closer to a set number. Okay, so we have a hole there. So we have a hole at, and we want to know what is the y coordinate for the hole. So let's go ahead and plug that x value in to our function that's reduced. 1 minus 1 over 1 plus 2. So that gives me 0 over 3, which is 0. Okay, so we have our hole at 1, 0. Okay, and then let's go ahead and look at what the other zeros mean. So the zeros of the denominator are going to be problematic x values. So we already handled the 1. You know, we can go ahead and cross off the 1. Let's use a check mark to indicate we did it. So we went ahead and handled the 1. We know what's happening there. It's a hole. Now we have to figure out what's happening at the 0 and -2. So in general, what happens when you have this division by 0 but the factor doesn't cancel is you have what's called a vertical asymptote. What's going to happen if you look at the pattern of the x values is that the x values are going to shoot up or down. It's kind of like there's a wall, and you'll be able to notice, oh, it's going to be positive or minus infinity, but you cannot plug in anything that causes division by 0, period. So we're going to have vertical asymptotes at x equals 0 and x equals -2. Okay, and just a note, because we had division by 0, but the factors didn't cancel. From the denominator. So just kind of comparing and contrasting, x equals 1, 2, x equals 1, -2, and 0 were all going to be undefined, but the difference between the hole and the asymptote is that the hole, the factor that went with the hole in the denominator, completely reduced out. So that is the distinguishing factor between vertical asymptotes and holes. Okay, so we've got pretty much all we can get from the numerator and denominator. Now, a great question that we might want to make a note of at this point is, how would you get an X-intercept? So usually that happens with zeros, right? But in this particular instance, the only way you could get an X-intercept is when you set your numerator equal to 0, But there's the caveat that the denominator can't also be 0. So you can't ever have division by 0. So when we set our numerator equal to 0, we would get x minus 1 equals 0, and we'd say, oh, we have an x-intercept at 1. But we already figured out that we had a hole at 1, 0. So there's none. Okay. And then let's go ahead and take a look at our next step, which was, let's see. Yes, we're going to check and see, do we intersect our horizontal asymptote? Okay, so when I look at my horizontal asymptote, we figured out based on the leading terms that it was going to be happening at y equals 0. So to figure out if you intersect a particular y value, you set your function output equal to 0, and you set your polynomial equal to that value that you want to know if you intersect. So if I had a horizontal asymptote at 5, I would write 5 equals. But since our horizontal asymptote we already established was at 0, we're going to set your reduced fraction equal to that. It makes it that much easier to do. And now we have a rational equation that we can solve. So one little shortcut memory trick that people call this is cross multiplying. It's the same as if you multiply by the denominator on both right and left. And I've had some very observant students comment that, hey, why can you cross multiply on an equality, but we couldn't cancel, we couldn't multiply by x on an inequality? And the answer there is an inequality is different than an equality. So for an equality, we can do this cross multiplying trick. So 0 times x plus 2 gives me 0, and then we get x minus 1, and we get that the only intersection point could be happening at x equals 1. Okay, so we've got an intersection at x equals 1, so we're going to intersect at the hole. Because we already established that at x equals 1 we have a hole. So once you figure out something's a hole, it's never not going to be a hole, if that makes sense. It's always a hole. It's just the curve's going to approach the asymptote and it's going to cross at one of those ghost points. So okay, with all of this, I think we have enough to at least take a preliminary look at the sketch. Okay, so the first thing I do with my rational functions is I'll usually graph the asymptotes and x-intercepts first. So I found out that my asymptote, I had an asymptote at y equals 0. So let's do that in red. Actually, let's do the horizontal asymptote not in red, because I don't want you guys thinking that you can't cross it. You definitely can intersect horizontal asymptotes. Okay, it's the vertical ones that you're never going to intersect. So there's our horizontal asymptote. Let's take a look at our vertical asymptote. We had one at x equals 0. And then we have another one at x equals 1. So let's scale our graph a little bit. Let's scale our graph at every 2 is 1. Every 2 squares is 1. There we go. Okay, so we have one at 1. We have an asymptote at -2. Okay, and then let's graph our x-intercepts. If we had any, we didn't. We just had a hole, right? So we had a hole at 1, 0. And now remember, when we figured out the intersections of the horizontal asymptote, we only got this hole. So I can't cross the blue line in any other point than the intersection points that I found. So you found them all completely when you do the algebra here. So I shouldn't be crossing the blue line any more spots than this ghost point that I just drew. And I already know I can't intersect the vertical asymptotes ever, because they're a type of behavior where the curve is going to branch off and approach them like a wall. So knowing that, when I go to graph this, what I'm looking for is basically I'm going to have graphs that's trapped in a region. So I could, my possibility one, like as I go left to right, I could have a curve that's here or a curve that's here. You can't have both because you'd fail the vertical line test, right? So I'm going to be a little bit like Sherlock when I do this and just use a lot of deductive reasoning. We're going to rule between top or bottom, top or bottom, top or bottom. Now this is I chose this example because it's not one of the easiest functions to graph, and we might need, I think we're going to need a little bit more information to get a clear picture of this. So there's a couple different perfectly valid strategies for doing this. One possibility that you could do to get more idea of the curve is you could do a sign chart. That's what our textbook author really likes to do. Basically, they like to do the inequality test because it tells you whether the curve is greater than 0 or less than 0, so above the x-axis or below. Or we could do a t-chart. Okay, and honestly, I really don't have preference between those two. I guess when I tend to do this, what I tend to do is, well, let's do a sign chart. Let's do a sign chart. So our reduced function was x minus 1 over x plus 2. And we want to know, let's say, okay, let's do a sign chart for it. We got -2, 1, -2, 0, 1. And we got our factors. Okay, so I'm going kind of quick because we've done this already with our inequality test. Okay, and with the sign chart, the cool thing is once you've done a few of these, you know how they go. Okay, so we've got that our graph is going to be negative, positive, negative, positive. Okay, so to the left of -2, we're going to be negative. So that means we are below the x-axis. Then we switch to above the x-axis. Then we are below. Then we are above. Okay, so that pretty much tells us in one chart where is our curve going to be at. So I know that I have to be trapped like this because I can't intersect the red or blue lines. So I have to be below. And then above must be trapped like a U. Okay, again, I'm going to stay away from blue and red. And then it looks like above. So, oh, pardon, from 0 to 1, I am below. So I have a little region to the left of 1, so I must look like that. 0 to 1, I'm below. And then above crosses like that. But, okay, be careful about what I just did. So I did that how I've seen some people do it, but what's wrong about this arrow? So the end behavior, I'm supposed to approach 0, and I just went ahead and I drew an arrow there, looking like it was going to go off to infinity. So instead, what's going to happen is this is going to come up, and then at some point, it's going to have to turn around and lie flat. Now this little bump, that little bump there is going to be something that you will find in calculus. So in calculus, you're going to learn these cool tests using the derivative that helps you find basically those peaks and valleys of the function. So this is by no means is an exact graph. This is definitely considered a sketch. But it's an important step for calculus. So I'm just labeling my axes there. So we've got our function. Let me use a different color just to kind of exaggerate how it's different from the x and y axis. Let's use this darker blue color. Okay, so there it is, there. And I really like the sign chart, but again, you don't have to do it. So I don't want you guys to think that there's only one right way to do these things. Pretty much, there tends to be more than one right way to do things. Okay, so there's our sketch. Okay, now let's take a look at what this looks like compared to something like Desmos. So okay, I'm kind of curious what Desmos would show us for this. Okay, so we're going to graph our original function. Make sure you use parentheses for your numerator and denominator. Now, personally, I really like Desmos and Wolfram Alpha as my top graphing calculators, but you'll notice that all graphing calculators kind of share the same shortcomings. So let's look at this graph compared to what we had. Okay, the biggest thing that I see right away, it's not showing the hole at 1, 0. Okay, it doesn't understand it at all. So what it's doing is it's approximating a curve. And you guys will learn a lot more about this in the calculus sequence, not necessarily Calc 1, but particularly Calc 2 and beyond. You're going to learn how graphing technology approximates points. It really doesn't know. So that's why it doesn't commit to a hole, it doesn't commit to an asymptote, and it just doesn't really do a great job of showing things. But if you know what to look for and you pair that with your knowledge, you can kind of tell that we did the right graph. So if we switch back to what our sketch looked like compared to this, okay, we have the right thing. Okay, see? Great. Okay, so I really love graphing rational functions because I feel like a lot of our tools that we've been learning kind of come together to pay off here, and it gives us an opportunity to kind of deeply understand the connection between the algebraic and the visual. So really dig this unit. Okay, let's check out another example. I'm just going to draw your attention to some patterns before we move on, some key patterns that we observed. Okay, so degree of numerator being smaller than the degree of denominator. That was a horizontal asymptote at y equals 0. And then when you observe that you have division by 0, your two possibilities are whole if it cancels, and a vertical asymptote if it doesn't. Okay, so let's take a look at another example. For this example, we're going to graph the function f of x equals 2x squared minus 3x minus 5 over x squared minus x minus 6. Okay, so again, we have another unfactored rational function, and before we go ahead and factor it, let's take a note of our degrees. So this one, purposely, like I said, we're going to explore all three possibilities. The three possibilities is that the denominator is bigger, the numerator is bigger, or that they tie. So this is possibility 2. We have degree of the numerator. By the way, when I write DEG, that's kind of a shortcut calculator notation for degree. The degree of the numerator is 2. The degree of the denominator is also equal to 2. So we have a tie. Okay, now what happens when you have a tie? If I were to go ahead and choose x equals 100 over x equals, like when I try and find my right end behavior and I plug in x equals 100, you would get something like 100 squared over 100 squared. Well, what's going to happen? Those cancel. So these fractions are going to approach a finite number, which is the ratio of your coefficients. So 2 over 1 in this case. So you're going to have a horizontal asymptote at y equals 2, which is the ratio of the leading coefficients. Okay, and you guys don't have to explain this to me necessarily on the test. You can just write that they tie and then say it's an asymptote at y equals 2 in this instance. I'm always writing more when I show you guys this stuff, so that's just my job teaching you. I got to explain why things are true. so you believe it and understand it, not just taking blind facts, right? So we're going to have a horizontal asymptote at y equals 2. If you don't believe me, keep on plugging in bigger and bigger x values. You're going to see we're going to approach 2. And if you plug in really, really, quote, large negative values, you'll see that we also approach 2. Okay, and then let's go ahead and factor the numerator. So the numerator, we have factoring by grouping. Looks to be, I'm not the fastest factor. You guys might have already factored that in your head, but sadly I lack that speed. So we have our a times c is negative 10. We're looking for two numbers that multiply to negative 10 and add to 3, 5 and 2. Make the 5 negative. So that tells me how to split up my middle term. And that tells me that I can factor this as 2x times x minus 5. X times 2x minus 5 plus 1 times 2x minus 5. So taking it in halves, and then we have a common factor of 2x minus 5. So with our factor by grouping trick, we get 2x minus 5 times x plus 1. So whenever you guys can factor, it's way faster than the quadratic formula. Don't want to knock the quadratic formula, but it is slower. It is more likely to lead to mistake. So factoring our function, we get 2x minus 5 times x plus 1 over, and then for the denominator, this one I can see how to factor that kind of quickly. X minus 3 times x plus 2 would get me where I had it. So this one's kind of cool because we don't have any repeat factors. Okay, so looking at that, we can use this to figure out the zeros of the denominator and numerator. Okay, so the zeros of the numerator are going to be 5 halves, negative 1. The zeros of the denominator are going to be 3 and negative 2. And we don't have any repeats. We don't have any factors to cancel. So in this case, anything that causes division by 0 is going to be the vertical asymptote. So because nothing canceled. So our zeros of the denominator, this means that we have X-intercepts at 5 halves, 0, and negative 1, 0. And think to yourself, are they going to be solid or open? They're going to be solid. They're actually points. The only time you would have an open is if you had a hole. And we already saw that that would have to happen if you also had that 0 in the denominator. So we got X-intercepts at the zeros of the numerator, and we have our vertical asymptotes at the zeros of the denominator. So x equals 3 and x equals negative 2. So notice the difference in notation there. Our x-intercepts are points, so I use coordinate form, and our vertical asymptotes are lines. They're like walls, so that's why you use the x equals notation. Okay, and then moving on, we've got everything we can get from that. We need to figure out, lastly, do we intersect the horizontal asymptote? Okay, so if you don't have a horizontal asymptote, don't worry about it because you don't need to figure out whether it intersects it, but we do. We have one at 2. So I'm going to take my function. The factored form is always easier to work with, by the way, when you have it, as you can reduce it first. Okay, so there is our equation, and if we multiply both sides by the least common denominator, you have the effect of doing that cross multiply, which gives me the following equation. So I get 2 times x squared minus x minus 6 versus 2x squared minus 3x minus 5. So I get 2x squared minus 2x minus 12 equals 2x squared minus 3x minus 5. So when I try and isolate my x values, I combine my like terms. If I subtract the 2x squared from both sides, I'm left with negative 2x minus 12. And is that equal to negative 3x minus 5? And then I isolate my x's. Let's move the numbers to the right and the x's to the left. So if I add 12 to both sides, and add 3x to both sides, I get x equal to 7. Okay, so I get x equals 7 for my intersection of the horizontal asymptote. So at x equals 7, I'm expecting for me to get the point 7,2, and we will check that. So we have an intersection at the point 7,2, and this is going to be a solid intersection because we don't have a hole at x equals 7. So, a little different than the last example. Okay, so let's take a look at what the graph would look like. And sometimes you can kind of deduce this without even really needing the sign chart. So we need our horizontal asymptote at 2. Actually, I'll go ahead and use the blue color again. Okay, so at y equals 2, we have our horizontal asymptote. We had vertical asymptotes at 3 and -2. -2 and +3. And then we had X-Intercepts. At 5/2. So 2.5. And -1. Okay, and then, okay, so the only other thing we had was a whole 1, 2, 3, 4, 5, 6, 7. Okay, so I expect there's going to be an intersection there. Okay, so I can kind of deduce a little bit from this. Now, this one's kind of cool because, again, the sign chart, very helpful tool. Don't want to discourage it. But you can use some deductive reasoning to tell you how this curve's going to go a little bit faster. So starting left to right, I know that I am not supposed to have an x-intercept. So if I try and fit my curve here, I produced an x-intercept. So take that away. Okay, it can't be there. It has to live up here. Okay, now when I go and I choose between top and bottom for the middle third, I already have x-intercepts down here, so it must fit like this. Okay, it must fit like that, because I know I can't cross the y. I can't cross the y equals 2 line, the horizontal asymptote, because I'm only allowed to cross there at 7, according to our algebra. So it must be trapped in that lower region, connecting the points between my y-intercepts. And then when I look at the third region, I cannot start off here. Because if I try and start off there and get up to 7, I'm going to create another x-intercept. And I already found my only x-intercepts. So I must start off here, and then it must go like I'm going to go down, dip, and then turn and come back up. Just like last time. Because I know that this curve should try and flatten itself off at 2. It's not going to keep going down to -infinity. It's going to try and flatten out along that line. But I know that I crossed at 7, and I know that I wasn't supposed to have an x-intercept to the right of 3, because I found my x-intercepts already. So through deductive reasoning, I can tell that the graph has to be like that. Now, I don't want to discourage the sign chart. That's why I say that that step is optional. Okay, if you do your sign chart and you test this, it should confirm the information we had here, which is we're going to be, well, yeah, I mean, it'll confirm the information we had here. The sign chart isn't going to help as much for the horizontal asymptotes being above 0, because it's only going to tell you positive versus negative, so there might still be a little bit of like, you might want to just find a couple points to help you out with that. Okay, so then we'll go ahead and check this with Desmos, just make sure that it looks good. Okay, So we see our horizontal asymptote chilling out at 2. Looks good. We see we have what looks to be a vertical asymptote at x equals -2. And another asymptote looks like it's happening here at 3. And let's see what happens at 7. Should be at 2. Yeah, at 7 we're at 2, so we found the right intersection point like we thought. And as we can see, the curve is going to go dip below 2 and then trend just slightly below that y equals 2 line, but it's not going to take off down to infinity by any means. It's always going to stay along that flat line. Okay, so it looks good. Let's move on to another example. Okay, so this is our third possibility right here. So my only possibilities are that I have, in terms of the degrees I'm talking about, we have our third possibility. So this is the case where the numerator wins. We'll see what happens. So the degree of the numerator is 3. The degree of the denominator is 2. So see where that's coming from, 3, 2. And that means that we have numerator wins. So when I try and look at the behavior here, I'm going to get 100 cubed over 100, or 2 times 100 squared, for instance, for the right end behavior, which would give me 1, 2, 3, 4, 5, 6 zeros on top. 1, 2, 3, 4. Okay, it looks like what's going to happen is the numerator is going to outstrip the denominator, and we're going to have something that's headed towards positive infinity. Okay, we're going to have a number that just grows without bounds. Doesn't mean that it grows fast. It just means it's going to take off. Now, there's a certain amount of detail that it can be beneficial to know in calculus, so I want to review to you guys how to find it, and there's a couple homework problems asking you to find it, even though I don't tend to emphasize this case where you do have the degree on top being bigger. I tend to focus on practicing graphing the other two cases a little more, but it's good to have this in the back of your mind, which is that when this happens, we're going to have what's known as a slant asymptote. So it means that the curve is going to try and behave like a line. It's going to try and lay flat along a line, but not a horizontal one that's slanted. So since it's headed towards positive infinity, it's going to be a slope with a positive slope line. Okay, so let's go over how to find it. In order to find the slant asymptote, basically what you do is you do a long division problem. So we learned in the last unit how to do long division and how to do synthetic division. And if you remember, we can't do synthetic division if we're not dividing by a linear factor. So because we're dividing by 2x squared plus 2, we're kind of stuck doing the long division here. Not kind of, we are stuck doing the long division here. So that's why we learned both of them. Okay, so now I need to look at my leading term 2x squared compared to my leading term x cubed. What I have to multiply the 2 by to get to the x cubed looks like I would have to multiply by an x, and then I would have to multiply by a half. So a half x. And then when I do that, it's always minus. I get positive x cubed. And then a half x times 2 gives me x. Just positive. Okay, leaving space for that negative 2x squared, we get negative 2x squared. 3x minus x gives me 2x. And then we repeat the process. 2x squared. To get to negative 2x squared, I would need to times that by negative 1. And then I would get negative 2x squared, negative leaving myself a little space for that 2x. Okay, so I end up getting 2x and then 0 minus a negative 2 is 2. Now, I look and I see that I have reached something that is smaller degree than what I'm dividing by. There's nothing for me to multiply. There's no polynomial I can multiply the 2x squared by to get to 2x. So because of that, I'm done with the division. And what we have ended up figuring out is that when we look at what we got a half x minus 1 and then plus 2x plus 2 over what you were dividing by. Okay, so this is going to be a cool thing that you guys talk about in calculus called taking a limit. But basically, the long story short is when we look at that last term, as you plug in big X values, it goes to 0. So this part goes away, goes to 0, and we're left with what is the slant asymptote. So we're going to be left with 1/2 x minus 1. Okay, so when I draw this line, it's going to look kind of interesting. It's not going to be horizontal. It's going to be a line that's slanted. Okay, so there's our slant asymptote. That's our end behavior. If someone asks, like, what was the end behavior for this, having that the right end behavior is positive infinity and the left is negative infinity is going to go hand in hand with that line that we draw. Okay, so then let's take a look at if we can factor these at all. Let's get the zeros of the numerator and denominator. So let's factor. To get there, factoring out from the numerator, we get x times x squared minus 2x plus 3. And then in the denominator, we get something that doesn't factor over r. So because it doesn't factor over r, it's not going to produce anything on the graph. We saw that a little bit with polynomials. It'll influence shape, but not really like any of the zeros. So, and it looks like we can actually factor that numerator one more step. We get x minus 3 times x. Can I factor it? I don't think so. Let's check it. B squared minus 4ac will tell me real quick if it has real zeros. So b squared is 4 minus 4 times a times, oh, it doesn't factor because it's negative. Discriminant being negative means we can't factor it. So that is as far as we can factor it. Okay, so when we take a look at our zeros of the numerator and denominator, okay, for the zeros of the numerator, we're only going to have 0 for our real number, and for the denominator, real zeros, there were none. Okay, so what that means is there are not going to be any x values that are real that we plug in giving us division by 0, which means we won't have any sort of vertical asymptotes, and we won't have any sort of holes that are being created. So no holes or vertical asymptotes. Okay, and then because we didn't have a horizontal asymptote, we had a slant asymptote. Finding the intersections for slant asymptote is, I don't need you guys to find that. Long story short, that process can be kind of complicated, and I just, it's not quite as necessary to get in this shape. So I don't need you guys to be finding intersections for slant asymptotes by hand. Okay, so let's graph this, see if we need to do that sign chart. Okay, so we had a slant asymptote at a half x minus 1. Okay, so it goes up 1 over 2. Come on. Waiting for it to give me that auto line feature. There we go, there's 1/2 of it. There's the other half of it. Nice. Okay, so there's our slant asymptote. And then where we don't have any vertical, do we have any x-intercepts? We do. Got one here. So I think what we're going to have here is something with a fairly interesting shape. And I was pausing because I was thinking, do I want to proceed with a sign chart or not? I think that this could be a great example where a sign chart might not be as helpful as finding some points on the graph. So I'm going to try and be strategic, and I think a T-chart method would be the most effective here. So T-chart is just your blind, kind of blind because you don't necessarily know what you're going to get, method of finding some points on the graph. So if you're on the graph, let's find some x and y points, and I want to try and find, let's plug in -1, 2, 3, 4, 5. Let's plug in -5. And let's plug in negative, that'll give us something on that side. Let's plug in negative or positive 5. Yeah, let's plug in positive 5. Okay, you can see why usually I tend to stay away from this method because it is a little bit more tedious. This is where technology can be really helpful, and I 100% do encourage you to use technology on these to assist yourself. I'm just kind of recommending that it's more of a checking tool, but you're not completely relying only on technology, because like I said, there are some shortfalls to the graphing technology, and also, as we already know, not all schools are going to let you have technology when you go on, and I don't want you guys to transfer to poly like I did and be kind of blindsided with your lack of technology, which I definitely was. So anyhow, let's go ahead and plug this in. Here's how I think is the most efficient way to plug this in. If you have a graphing calculator, you can graph it and use the T-chart mode, or if you're using something like Desmos, which a lot of you guys are because the pandemic and just not having funds to spend on one of those cool graphing calculator bricks. Okay, here's the numerator, 2x squared plus 2. Okay, yeah, I thought it was going to be kind of cool looking. So see how it is kind of like, it's like a line with a weird bump to it. And you would not really be easily able to guess the equation of the line without finding the slant asymptote. So it's cool that we know where it's trending towards. And let's take a look at where we'd be at 5. 1.731. And then at -5, we'd be at -3.654. Okay, so this is going to feel a little bit interesting because either you're allowed technology or you're not allowed technology. If you guys had technology at this point, I would suggest that you just kind of switch over to your technology to graph this. If you weren't, you would have to just calculate these by hand, which is something that I did have to do as a student at Cal Poly in a lot of math classes. So the -5, we were at -3. So we were here. And then in a little bit, I guess a little bit more than that. So we were like down here, slightly below. And then for 1.7, or for 5, we're at 1.731. Okay, and if you did want to actually check the intersection of the slant asymptotes, like it is possible to do. I'm kind of curious, so I'll check it, even though I don't require you guys to do this part. If I had a half x minus 1 and I want to know where does that line intersect my curve, I would set 1/2 x minus 1 equal to my original, which is x cubed minus 2x squared plus 3x over 2x squared plus 2. And I want to have this as one fraction. So this would be like having x over 2 minus 2 over 2, x minus 2 over 2. Okay, and it's just by taking something that was two terms, getting a common denominator. Okay, and then cross multiplying that is going to be kind of a beast. 2x cubed plus 2x minus 4x squared minus 4. And is that equal to 2x cubed minus 4x squared plus 6x? So we take away our 2x cubed and add our 4x squared. And we get 6x equals 2x minus 4. So that would be at x equals -1, we appear to have an intersection. So it would be here. Okay, so I could improve my curve a little bit having that knowledge. So knowing that I intersect at -1, I can make this sketch a little bit more refined and look like that. Okay.